Hey guys, today we're going to do Kinetics, which is chapter 14. This will be the last chapter before our exam 1. Okay, and this one, the only thing that we're carrying over from chapter 13 is going to be molarity. Okay, so just some background on kinetics. I just really want you to know that kinetics is a study of the factors that affect, the factors that affect the rate of chemical reactions. Okay, so really in kinetics, we're going to be talking about how fast a reaction happens. Later, we'll talk about if it happens or not. Temperature is one of the common things we talk about that affects the rate. Okay, and then the speed of our reaction is called the reaction rate. Okay, and that rate is a measure of how fast the product makes, or the reaction makes products from the reactants. Okay, this one's going to have a lot of graphs, a lot of tables, things like that. And we want to be able to control the reaction rates. Okay, a major piece. The greater the concentration, the faster the reaction will happen. Okay, that means you're going to have more stuff in your container. So you've got that greater concentration. And so it's more likely that it will happen faster because you've got more stuff in the container. Also, when you increase the temperature of your reaction, okay, you're going to increase that rate. It is about every 10 degrees increase, the speed doubles. You don't need to know that math value, but just remember from chapter 11 when we were talking about gases, when you increase temperature, the particles start speeding up and that's when they go from liquid to gas. And when they're in a gas, obviously they're going faster, and the faster they're going, the more likely they are to hit each other, and that would cause the reaction to happen if they hit the correct way. Also, small molecules are going to react faster than larger molecules because the likelihood they're going to hit the right way. Also, gases are going to react faster than liquids or solids, and again, that's just because they're going faster to begin with because they're in gas form. So rate specifically is how much quantity changes over a given period. Okay, so in this image to the right, you can see we've got A and B are changing to C, and as we go, notice this one is pretty quick. It happens within the hour that you're going. All the A's and B's convert into C, your product. The one on the far right has a much slower rate. As we watch it happen through the hour, it's not all turning into Z, these ones. Only 3 of them have changed over. And that's okay. The reaction is happening. It's just happening at a much slower rate. And you're going to see this in one of our labs. All right, so as we're going through this reaction rate, just remember that we're always going to use up our reactants, and because of that, we're going to put a negative sign in front of this rate equation because our reactants are going to decrease in concentration over time. Okay, also, so you know, from here on out, brackets mean molarity. So notice here we've got I2, it has brackets. That means the molarity of I2. And delta is just the change in, just like everything else, final minus initial. Same thing with time. Here we see an image. Notice the products are increasing over time, and the reactants are decreasing over time. Do note we're missing a reactant. That's okay. This is just showing you that it's a function of time, which is concentration over time. Okay, we will normally use the average rate, so we're going to take the linear approximation. Sometimes if you have to pull an instantaneous one, a slope at that one point, we'll use a different calculation. And that instantaneous rate is determined by taking the slope of a tangent line to the curve of that particular point. which is what the triangles are for. We have to extrapolate a line at that specific point, not being an average. In calculus, that's a derivative. We're not doing calculus at all. We're just going to use algebra. Okay, most reactions have coefficients. So up here, we've got a 2 coefficient. Down here at the bottom reaction, they're showing coefficients, but it's the little letters are our coefficients. So remember, our reactants are going to have negative signs, but we are going to have to show our stoichiometry through this, through our coefficients. So the coefficient goes into the bottom denominator. Okay, and all of these rates will be equal because we're calculating them for the same reaction. Whatever D is or C, we don't know. So up here in the top one, our rate would equal negative, well, that one's just the change of H2 over the change in time. The next one is negative change in I2 over the change in time. The last one, our product would be 1/2, and it's going to be positive delta HI over delta T. It's positive because it's a product, and this 2 comes in because it's got a coefficient. If it does not have a coefficient, you don't have to put that. But I know this appears on the homework. Okay, so here we're just putting in numbers over that amount of time, and then we're applying our coefficients in, like this 2 appears down here at the bottom. So in the first 10 seconds of a reaction, the concentration of I drops from 1 to 0.868. So here's our I. Calculate the average rate. So we're looking at rate. Remember, sorry, it's final minus initial. So it's 0.868 minus 1 over our 10 seconds. And this is a reactant, so it's going to be negative. Okay. Don't forget the 2 negatives are going to cancel out. That's okay. All we're doing is plugging it into that equation. So now we're determining the rate of change of H over that same time interval. So remember, all of our rates are going to be equal. It wants the rate of change of the concentration. So the whole thing is going to be equal to 0.0044. And hydrogen is negative 1/2, and then 10 goes on the bottom. And I'm looking for this initial value, this part. Okay. Of course, my calculator is not doing what I want it to do. Okay, I get 0.088 is equal to -1 of the H plus. So H plus is going to decrease at -0.088. Molarity is its rate of change. Okay, that's the same. Oh, they didn't plug in the time. Okay, so I had negative 8.8 times 10 to the negative 2. Theirs was ignoring time. They left time as a factor, and I plugged it in. So make sure, so my unit was molarity, theirs was per second. So if I would divide my answer by 10 seconds, it comes out to the same thing. So just make sure you're paying attention to the units. On Mastering Chemistry, it's going to give you the units. Okay. All right. Rate law. So that was rate, finding the rate specifically. Now we're going to start writing rate laws, and they're always going to be determined experimentally. This is a huge part of kinetics, y'all. Okay, and you always write the rate is equal to the reactants to their order times K, which is called a rate constant. Okay, and you will either be given it or you will calculate it. And it's only the reactants. We do not write the products in the rate law. Okay, the exponent on each reactant in the rate law is called the order, and the sum of all the orders is the overall order. So like in this example, we've got 2 here, which means there's a 1 implied here. So the overall reaction order will be third order. Also remember, you can write the 1, but you don't have to. I normally don't. Okay, so we're going to go through what these mean for orders, and then it's going to make a whole lot more sense once I do one with you. Okay, so 0 more order means the rate of the reaction does not change when I change concentration. Okay, so anything to the 0 power, remember if you do that in your calculator, it's times 1. And so that means it stays the same. The units also stay the same as the rate. Molarity over seconds. K is molarity over seconds. First order. That means whatever I do to A will also happen to my overall rate because the concentration of A is affecting my rate. Okay, my rate is always molarity per second. It could be a different time unit, but it's normally not. The unit for K is seconds to the negative 1. There will be a shortcut later on. For second order reactions, that means that I'm squaring the concentration. So when I double A, it's going to square it, which means it'll quadruple the rate. Okay, again, the rate unit is the same, but the unit here is a little different. Okay, changing the concentration of each reactant will affect our rate law. And by doing this, the effect of each reaction's concentrations on the rate can be determined. And we'll see results, we'll look at the differences, and we'll compare them. Okay, so here I'm going to do our first example. Remember, we're only looking at the reactants. Okay, so first, I'm going to write the basic rate law. You should always do this first. Rate is equal to K. And then we've got our 2 reactants, NO2 and CO. Actually, I'm going to make sure. I need to leave room for our exponents to go into that rate law. So what we're going to do is look where 2 of them are the same in 2 different experiments. So like CO is the same in experiments 1 and 2. So that is not affecting our rate. So here I see that NO2 doubled. And the rate quadrupled. Okay, the way to determine this is, sorry y'all. I've got 2 to the x, that's our order. It's going to be 4. So I'm looking for this piece. Hopefully you know that 2 squared is 4. And if that is the case, NO2 is second order. Okay, the next thing we're looking for is when when NO2 is constant. So we can cross out 2 and 3. CO doubles here. But here, notice that it pretty much stays the same. Not 0, it's 1. So we're looking for 2 to the x is 1. Okay, remember anything to the 0 power is 1. So this is 0 power. So really, this is rate is equal to K and then just NO2 because CO is not affecting our rate. Okay, and again, if you have questions, I will absolutely love to help you with this. Okay, it also wants us to find the rate constant. So once we do that, you can pick one and we're going to plug in values. So I've got my rate is 0.0021 is equal to K. That's what I'm looking for. Let me go ahead and add our units in. This may help us later on. Remember, brackets mean squared, brackets mean molarity. So I've got 0.0021 divided by 0.01 divided by, 0.01. Okay, when I do that, I get 0.21. So K is 0.21. Okay, my units originally were molarity per second, and then I divided it by a molarity squared. So from unit analysis, which hopefully some of you did before, I can cross out one molarity because they're the same on top and bottom. So left, I have a seconds on the bottom and a molarity on the bottom. So you can either write it like this, 1 times molarity and seconds on the bottom. Most of the time, though, it'll be written like this. Remember that -1 exponent means it's in the bottom. Okay. Also, sometimes, remember molarity is moles per liter. So sometimes I'll go ahead and invert that molarity, and it'll be liters over moles per second. Okay, so it could be written either of those ways. Okay. I'll walk us through. All that determines it's 0. Okay, and there's our K value, which we did calculate with our units. Okay, the shortcut for units is going to be look at your overall order. So remember this overall order was 2. Okay, so our overall order is in. Let me write that. So it'll be molarity to the negative n minus 1 times time to the -1. So this one was 2 minus 1, so it was just 1. So it was molarity to the -1, whatever our time unit was. Just remember, time is not always seconds, it's normally seconds. Okay, so here we're going to do the same process we did before. I'm going to cross these out. They're the same. I'm going to say that doubled. And this also pretty much doubled. So my rate is equal to remember, if they're the same, it's 2 to the x is 2. That means it's to the first power. Then I find another one here. They're the same. I've got doubled. This is not doubled or quadrupled. It's not an easy number. So when that occurs, you need to go ahead and divide them by each other. So I'm going to divide 0.0098 by 0.0069, and I get 1.42. My arm is messing with it. Okay, so this one's a little harder. Okay, that's not an easy number. However, if you take the square root of 2, it comes out to 1.41, and it was not exact. So this is going to be to the half power, which again kind of messes with everything. This is the worst kind of power y'all are going to encounter. You're not going to encounter any ones that require you to use log. Okay, once we do that, you find k the same way. You plug in values and solve for k. All right, then we get to integrated rate laws. Okay, this is really at a specific point instead of an overall reaction. So this is applying calculus knowledge, but we're going to do it with algebra. So there are different ways to do it. We have our first order reactions. Our rate law is basic like this. I don't know why that keeps... Okay. Our integrated rate law is going to pull in the natural log. ln is natural log. Okay, I sometimes write that integrated rate law as ln at minus ln AO is equal to negative KT. So just keep in mind, I will probably write the one I just wrote at the bottom because that's the way I learned it. It's the same equation, it's just got both ln's on the same side. It doesn't really matter which one you use because mathematically it's the same. Okay, if you encounter a first order reaction, the slope's going to be negative K. It will always be going down. The half-life equation is important. So half-life is super important in first order reactions specifically. That's the only kind I'm going to ask you to solve. And that 0.693, it's the ln of 2. That's just a constant. And then K is changing with your different values. All right, so here we need to show that the reaction is first order, determine the rate. Okay, so the easiest way to show that the reaction is first order is to plug this into Excel and then graph it. Because remember, the first order graph is ln versus, well, ln of A versus time would be a straight line. That is the easiest way to go. I'm not going to ask any like this, but here, notice they plugged it in after using, I'm sure they used Excel. Yep, they talk about using Excel, and then you just pull the slope from the y equals mx plus b equation. Okay. So they wanted us to extrapolate data, but let's say we don't have a graph. Okay, so let's say we know it's first order. Okay, they told us our rate constant, which is K. They told us our initial concentration, and they told us our time. Okay, so I'm going to say ln of AT, that's what I'm looking for, minus ln A of our initial, so 0.0225 equals negative 2.9 times 10 to the negative 4 seconds to the negative 1 times 865 seconds. Okay, y'all, I've got to go get my calculator, so hang on just a minute. Let me see if I can pause. Nope, no pause. Okay, I'll be right back. Okay, y'all, I'm back. Sorry, I didn't think about a calculator when I started this. So I'm going to do, LNAT is equal to, I'm going to go ahead and move my LNAO over after I put it in. All right, so the unit for this is going to be molarity. I did that, I moved this over, so I plus this over here, and then I multiplied it by these two. Okay, to get rid of Ln, you need to use the small e function on your calculator, and that cancels out Ln. So I do second Ln, I don't know what your calculator says, so I get that AT, which is at that specific time, 0.0175 molar. Okay, so the molarity of our SO2Cl2 at 865 seconds is 0.0175 molar. And there it is down there at the bottom. All we're doing is plugging it in, make sure you've got it. Okay, here's another one, first order. What is the cyclopropane concentration after the same amount of time? But notice this one is minutes. And up here, our unit is seconds. So the first thing we need to do with this one is convert our minutes to seconds by multiplying by 60. So this is 14,100 seconds. Okay, we're going to use the ln. I'm going to use the equation they gave you. Because the way they have you solving this one is easier. Okay, so also notice there's no temperature in this equation, so as long as it stays at the same temperature, we don't have to take that into account. So I've got LNAT equal to negative 3.36 times 10 to the negative 5 times 14100 seconds plus our ln of 0.0445. Okay. Okay, I get that my LNAT is negative 3.59. And again, do the e to get rid of the ln, and I get that the concentration of AT is 0.0277 molar. So at 14,100 seconds, our concentration is down to 0.277 molar for our cyclopropane. Okay, second order reactions are going to be the reciprocal, 1 over the concentration. That one's going to be our straight line. Slope now will be positive K. Half-life equations are not really used, but just in case it pops up, maybe on an extra credit question, it's 1 over K times AO. Okay, so here they want us to do graphic analysis. They must have given us some data, which we didn't see. So we show it's not first order by graphing. It's not. So the ln graph didn't work. So then we graph it 1 over. We see that the reciprocal graph does work. And then they wanted us to extrapolate the data. Remember, K is positive 0.255. Okay, zero order is just the concentration versus time. Slope will be negative K because it's a downward slope. And again, half-life, this half-life isn't really used, only first order, but it's AO divided by 2K. Okay, this is a super important slide. Because I'm in video form, I can't tell you what slide this is. It's in the 30s, I know, but this is like a brief overview of all rate laws, integrated rate laws, what your units are, all of it. This will be an important slide to have when you're taking your test. I think it's like 35, but I'm not 100% sure. Okay, half-life is a practical application. This is how we calculate how much radioactivity how much it's decayed, how long it's been there. This is commonly used, things like carbon dating. Okay, so carbon dating's half-life is like 50, 100 years or so. So that's how we date fossils. As long as they have some of that carbon-14, we can see how many half-lives have expired, and so then we can tell how old it is. Okay, but it is literally the amount of time it takes for the concentration to fall to half of its original value. Remember, first order is the only one I'm going to ask you to calculate. It's 0.693 over K. Okay, here's the other two, 0 and second order, but again, normally we don't use those. Normally, half-life is first order. All right, so they gave me temperature. Temperature doesn't matter as long as they don't mention it again. It told me K. Remember, the equation is T half is equal to 0.693 over K. Notice this is seconds to the negative 1. 0.693 does not have a unit. So then my unit comes up, and I have 2.56 seconds. Okay, that is a very short half-life. This one says first order reaction has a half-life of 26.4 seconds. How long does it take for the reaction to fall to 1/8? So remember, it falls to half, that's one half-life. And then it falls to a fourth, because you half it again, that's two half-lives. And then it falls to an eighth. So we went from 1 to half, one half-life, 2 half-lives, 3 half-lives. It took me to get to 1/8 of the original material. Okay, it told me our half-life is 26.4 seconds. Wants to know how long. So at this point, we just have to do 26.4 seconds times 3. And I get 79.2 seconds. Okay, so again, very short half-life there. And that is it for today. We will talk about some more stuff next time. Have a good day.